In this video, we will utilize the definition of the mole to determine how many moles of anions are in 35.6 grams of aluminum fluoride. So this problem actually exploits two definitions of the mole. One of them is the part over whole relationship that designates the mole. That is to say, we have 1 mole of Al in 1 mole AlF3, again, part over whole. You can also say we have 3 moles of F over 1 mole of AlF3, again, part over whole. These are conversion factors. Another definition of the mole that will also be utilized in this problem is Avogadro's number. Anytime you see ions, anytime you see atoms, anytime you see anions or cations, you're going to have to use Avogadro's number. It's a very large number to designate how much is in 1 mole of that molecule, ion, or atom. So I think this gets best explained by actually doing the problem. All right, so first of all, you start with what you're given, 35.6 grams of aluminum fluoride. So 35.6 grams of AlF3, converting it to mole. The grams of AlF3 cancel out with the grams, so that's an important theme throughout this book, throughout this course, excuse me. We're left with moles. Okay, now this is where I want to tell you about the first rule or definition of the mole. It's part over whole. So as we said before, we have a relationship. For every 1 mole of AlF3, there's actually 3 moles of fluorine F. So why am I pinpointing on fluorine? Is because this problem is asking for moles of anions. Anions are negatively charged particles. So fluorine is F minus. The halogens are always going to be F minus, minus 1 charge. And Al is going to have always a plus 3 charge. So this is definitely where you want to use those flashcards to know what type of ions these elements like to form. As far as the halogens are concerned, it should automatically be registered to you that there will always be minus 1 in charge. And that also includes fluorine because it's a halogen. So our next conversion factor is part over whole. For every 1 mole of AlF3, there's going to be 3 moles of F. So for every 1 mole of AlF3, there is going to be 3 moles of F. You can actually say F minus here because it is an ionic compound composed of Al plus 3 and F minus. And now this is where we can use Avogadro's number because for every 1 mole of F minus, there's Avogadro's number of ions. Okay, so for every mole of F, there's Avogadro's atoms of F. For every mole of anion F minus, there's Avogadro's number of anions F minus. So this is where we use Avogadro's number. Okay, when we're dealing with ions, when we're dealing with atoms, when we're dealing with particular elements, how many atoms are there, how many moles of atoms are there, how many moles of ions are there. That is when you want to employ Avogadro's number. How many molecules are there? Again, that's where Avogadro's number comes into play. That's a constant 6.022 times 10 to the 23. All right, so 1 mole of F, or I guess you can say F minus, is this many ions of F minus. You can also say 1 mole of F has this many atoms of F, but the problem, it's specific, is in that it's interested in anions. And so the moles of AlF3 cancel out with the moles of AlF3. The moles of F minus or F cancels out with moles of F or F minus. Again, I want to emphasize and reiterate this could be atoms of F or ions of F minus. So let me just make it clear by putting an F minus here. So doing this on my calculator, and I'm getting a value of 7.69 times 10 to the 23 ions of F minus. Okay, that's the anion. So if we want to figure out how many moles of cations, Al plus 3, we would do pretty much the same thing here. Instead, it would be 1 mole of AlF3 to 1 mole of Al, and then 1 mole of Al plus 3 has that many ions, Avogadro's number of ions of Al plus 3. This problem is important because it utilizes not 1 but 2 definitions of the mole. Okay, the first definition of the mole, I'll highlight this in green, as a conversion factor that's part over whole. So this is the part, that's over the whole, and I put it that way to get the units to cancel. And of course, Avogadro's number is the other relationship for the mole. I'll highlight that conversion factor in blue. And so this is a powerful problem in that it exploits two definitions of the mole.